Hello, everyone. Thank you for joining us for today's Deeper Talk seminar. My name is Jared Heiss, and I'm the Science Director at SURF. Before introducing our seminar speaker, a few housekeeping items. Today's event is online. Questions will be answered at the end of the presentation. Raise your hand in Zoom to ask a question live. You can also use the Q&A button at the bottom of the Zoom screen. This talk will be recorded and available to view on the website institute.surf/deeper-talks, as well as on our YouTube and Vimeo channels. If you wish to receive a notification for upcoming monthly talks, go to the Connect link at the top of the Institute web page. Now it's my privilege to introduce today's speaker. Dr. Stephen Sekula is the Research Group Manager at SNOLAB and Professor of Physics at Queen's University in Kingston, Ontario, Canada. He earned his PhD in Physics from the University of Wisconsin-Madison after completing his Bachelor of Science at Yale University. He held postdoctoral research positions at MIT and The Ohio State University and was a professor of experimental particle physics at Southern Methodist University in Dallas, Texas, from 2009 through 2022. Dr. Sekula's primary research areas are in the study of neutrinos and the search for dark matter. He is co-spokesperson of the Helium and Lead Observatory, HALO, Supernova Early Warning System Detector, and recently concluded a term as Science Board Chair for the PICO Dark Matter Search Experiment. He's particularly proud of the excellent high school, undergraduate, and graduate students and postdoctoral researchers that he works with in his research programs. He previously worked at the Large Hadron Collider at the CERN laboratory and is a co-laureate for the 2025 Breakthrough Prize in Fundamental Physics for his contributions to that program. Dr. Sekula is also co-author or author of several books, including an advanced textbook for graduate students, the Dark Matter Discoverer's Guidebook, written with his spouse and colleague, Dr. Jody Cooley. Now let's get ready to head under the Canadian Shield to learn about SNOLAB. Dr. Sekula.
Yeah, thank you very much, Jared. It's a real honor to be welcomed back by both the Institute and the Sanford Underground Research Facility to share with you the SNOLAB research portfolio and the 15-year plan for the laboratory itself. It started as a vision, but it crystallized when it was submitted in its final form back in September, and I'm going to share that with the audience here today. So in order to introduce you to the SNOLAB research program, I have to welcome you to SNOLAB. And after I do that, we'll talk about the many research areas at the laboratory. While it has a core mission, the portfolio is fairly diverse at the laboratory, and that will lead very neatly into the 15-year plan for the laboratory itself. So let me begin by welcoming all of you to SNOLAB, the extremely deep, extremely clean underground laboratory in an operating mine. So to begin our visit to the laboratory, we have to get to the region of Greater Sudbury in Ontario, Canada. This area is about 4 hours north of Toronto. So a trip to SNOLAB usually begins with a flight from somewhere to Toronto. And then you can take a connecting flight to the Sudbury Airport, or you can drive and enjoy the beautiful scenery of this part of the world. Now, the reason that a deep underground laboratory is in Sudbury is because there are mines in Sudbury. And there are mines in Sudbury because of the deep geological history of this region. A close observer of this map may have already noticed that there's an interesting lake, Wanapite Lake, up here in the upper right quadrant of the image. So I'm going to go ahead and circle that. And the reason that looks interesting is because to somebody who has studied a little bit of geology, a little bit of the history of the Earth, you might recognize that this looks a little bit like an impact crater from an asteroid. And in fact, it is. It's a few hundred million years old. It's a fairly recent strike in the history of the Earth. The Earth is 4.5 billion years old. But actually, that's not the most interesting feature of this. The most interesting feature of this is the much bigger and much older crater, which is actually ringed here. Now, the reason it doesn't look like a round asteroid impact crater is because it happened about 2 billion years ago. And since that time, the continental masses on the surface of the Earth have stretched, they've split, and so this has sheared out this once round crater into something that's much more oval shaped. Now, the center of the crater is an area that is known as the valley. There are many towns out in this area where people who work at SNOLAB live. And that whole valley is ringed by a rise of rock. And that rock is the debris that rained down when the meteor strike occurred. So that meteor strike was extremely, extremely powerful. If there had been complex forms of life on the Earth at the time, they probably would have become extinct, the way that the dinosaurs, for instance, did. But at the time that this happened, there were only fairly simple forms of life on the Earth. And so extinction was probably not in the equation for them. Nevertheless, this impact was of sufficient force that it penetrated the crust of the Earth and went into the mantle and upwelled molten mantle material, which is rich in nickel and copper. And so the reason that there are mines in Sudbury is because mining on that ring around that valley is a relatively straightforward way, although mining is not easy, to access the nickel especially and the copper ore that was upwelled by this event. And SNOLAB is located down here next to this area marked Creighton. We are in fact located in the Creighton mine, which is operated by the Vale Base Metals Corporation. And its primary mission now is to bring nickel out of the ground and bring it to market. Now, that's not SNOLAB's mission. This illustrates that impact crater I just showed you. And you can see here the different colors indicate the different densities and kinds of rock, the different kinds of minerals and materials that are to be found. And you can see there's a wealth of mining activity around this crater that has existed historically. Now, people didn't appear here only when mines appeared. The story of people in Sudbury is a much older story, and I'll come back to that in a minute. SNOLAB is located on the traditional territory of the Robinson-Huron Treaty of 1850, and it's shared by the indigenous people of the surrounding Atikameksheng Anishinaabeg First Nation as part of the larger Anishinaabeg Nation. And one of the important things that Canada is doing right now is it is going through a truth and reconciliation process where it recognizes that those who are on the land now are not necessarily the people who have always been on the land in the past. And the people who live in the region we now call Canada can trace their history back 15,000 or 20,000 years when people first crossed over from the Asian region into the American region. We acknowledge those who came before us and we honor those who are the caretakers of this land and the waters. The land that we're on is also known as Niswakamuk, which is a word that effectively translates into something like the place where three roads meet. And Sudbury itself is a crossing point of many people and many roads. There are many different cultures that call it home now. There are many different facets of human life that cross there, the arts and music, industry, and science. And SNOLAB is focused on the science mission, although we are entangled in the industrial and in the artistic as well through our program. So let's go to SNOLAB. If you come to the Creighton mine site and you cross into the industrial zone, the first thing you'll encounter that is a part of SNOLAB is our surface complex. So this is the building here. It's a fairly typical looking office building, although it is also home to laboratory spaces. And the idea then is that to go to the crown jewel of the site, which is the underground clean laboratory, you first have to suit up in personal protective equipment because this is an industrial mine site. It is an operating mine environment. So there are regulations that govern our behavior here. And then you would walk, it's about a 2-minute walk from the SNOLAB surface building over to what is known as the number 9 shaft. Shafts are vertical tunnels on a mine site. Drifts are horizontal tunnels on a mine site. So we're going to take a cage down and we're going to go down 2 kilometers, so over a mile underground. And then we're going to walk about another mile, about 1.4 kilometers, 1.5 kilometers or so from the place where the cage brings us to the place where the laboratory actually is located underground. This is our elevator. It is a double-decker elevator. Each deck of this can hold 40 people. It can hold more if you're really scrunched together, and we do have protocols for loading these cages so that you can fit the maximum number of people in it. Remember, this is an active industrial mine site, so we share that cage with the mining team, and we all have to get to work. And so part of the protocol here is getting in quickly and getting down underground quickly. We go 2 kilometers deep in about 4 minutes. That's extremely fast. And because the pressure changes, it increases by about 20%. The air pressure increases as you go down. You do experience similar effects on this cage ride to what you would experience in a pressurized jetliner cabin as it begins to take off and ascend into the atmosphere. The pressurized air puts pressure on your ears, and you have to kind of move your jaw, yawn, chew gum, something like that to release the pressure. This is a pretty normal experience for going underground at the laboratory. And where are we headed? We're going from the number 9 shaft building, which is located up here on the surface, the black building in the upper top left quadrant. We're going down actually through the vein of ore to the 6,800 foot level. And then we walk, again, we'll pass through the vein of ore when we do that, over to the location that is designated and owned by SNOLAB. And again, this is 6,800 feet underground. It's over a mile. It's about 2,000 meters underground, under this dense Canadian shield rock that we will benefit from for our scientific program. This on the right-hand side is a map of SNOLAB. I'm going to come back to this momentarily, so don't worry about this right now. I'll indicate the key features of the laboratory itself in a moment. But let me begin by sharing with you what a day at SNOLAB would actually look like. So again, we begin on the surface here at the complex. We dress up in personal protective equipment, and then we are going to make sure we bring important things underground, like food. We don't have food service underground, so you have to pack a lunch. We take the cage down. It goes very fast, and then 4 minutes later, we're down on the 6,800 level, and then we have about a mile walk from the cage station to the laboratory. And here you can see the staff approaching the entrance to SNOLAB. Now, we are now covered in mine dust. That mine dust is rich in things like uranium and thorium because it's made of dirt, and all dirt has that stuff in it. We need to get that stuff off. We wash it off our boots. We wash it off ourselves. So the first thing everybody has to do is wash their boots, take off their personal protective equipment, go into men's and women's dries or locker rooms, take showers, and then they change into clean room clothing, because this laboratory is a class 2000 clean room environment, which is an industrial standard for minimizing the amount of particulates in the air. So the first thing everyone usually does while the lab is being opened up for business for the day is they sit down, have some coffee, maybe have a breakfast or a second breakfast. You have to get up at early in the morning to catch the 6:30 a.m. cage to go to work. And then you can enter the lab complex. And what's amazing about this is we went from these dirty rocky mine drifts, which are normal in the Creighton mine, to these industrial looking spaces within a class 2000 cleanroom environment. Behind these walls are the same rock that the miners walk through in the morning, that we walk through in the morning, but you'd never know it because we have sealed it over with concrete, sprayed that over with shotcrete, troweled it so it's smooth, and painted it so we can put experiments inside this tightly controlled environment. I'm going to walk through some of these experiments here, so I'm not going to let the video roll too long, but there are some places in the laboratory that are so clean, even cleaner than the lab, that you have to take an additional air shower to blow dust off of you before you go in. So let's talk a little bit about the research at SNOLAB. And again, I'm going to come back to the map of SNOLAB in a moment as part of this piece of the presentation. So right now we're being guided by an overarching science strategy. We are in another phase of a multi-year strategic plan. And as a result of that, we revisited, what's important to the community, what's important to the laboratory a few years ago, and that all boiled into this strategic plan, Reaching New Heights Deep Underground, which is our plan for the period of 2023 to 2029. The science at SNOLAB is currently focused primarily on fundamental particle physics, but we do have a fairly rich and diverse overall program that grows more rich and diverse every year. So we're primarily looking in particular in two critical core questions at the frontier of science, astrophysics, and physics. What is the nature of the dark matter that seems to make up 85% of the matter of the universe, but whose constituents are unknown? And what is the nature of the neutrino? The neutrino is the cousin of the more familiar electron. But unlike the electron, which has a tiny little bit of electric charge, the neutrino has no electric charge. It feels only one of the 4 fundamental forces of nature that we know about so far. So it's very difficult to actually capture it and detect it, but it is ubiquitously produced in a range of processes, from the decay of radioactive isotopes in the core of the Earth and the mantle and the crust of the Earth, the dying of stars, nuclear power, many things produce neutrinos just as a natural byproduct of existing. And so studying the neutrino, because it's so important to the universe, is a really critical component of the frontier of our field. Now, we're widely interested in collaborating on scientific research that, generally speaking, requires a shielded, clean, deep underground environment. Neutrino observatories are among the things, of course, that benefit from this. They're looking for ultra rare things happening in an active detector volume, but you have to shield out all the noise so you can see the thing you're really interested in. We're also studying the effects of radiation or the lack of radiation on biological systems. We do environmental monitoring on our own and in partnership with agencies like Health Canada. And we look at the effects of radiation on quantum technologies. And I'm going to touch on all of these in the next part of the presentation. There are many disciplines represented at SNOLAB is really the bottom line. There's the obvious thing, physics, but there's a lot of chemistry. There's a lot of biology. We need industrial scale processes to realize the science goals of many experiments. So that's in the mix. Computation for modeling systems, optimizing systems, predicting what's needed and what's not needed for the next step of an experiment. That's critical. We do some geoscience. We work on environmental monitoring. We work on education and outreach within our communities, and we also benefit from engagement with the cultural arts aspects of both the greater Sudbury region and the surrounding regions. And if there's curiosity about any of that, I'd be happy to talk about that at the end, but I'm going to focus on the scientific program today. So here is SNOLAB at a glance. I don't expect you to memorize all of this. There's no quiz at the end of this. What I want you to take away from this is that SNOLAB, as it's currently constituted, is very busy and very full. So the key components of the laboratory, we'll start over here on the right-hand side. When we walk in the morning in our personal protective equipment, we're walking through this area marked utilities before we turn into this last long horizontal tunnel or drift that takes us to the entrance of the laboratory, which is located right around here at the center of the map. So when you go in there, you take your shower, you go into the refuge area, and then you are free at that point to go anywhere else in the laboratory. There are two major parts of the laboratory. There's the original part that was built for the Sudbury Neutrino Observatory, which is located in this cavern here in the lower left quadrant. SNO, or the Sudbury Neutrino Observatory, was a breakthrough neutrino observatory that, along with the Super Kamiokande experiment, shared the 2015 Nobel Prize in Physics for the discovery that neutrinos oscillate, and that this implies that they have mass. This was a breakthrough discovery. Other work at SNOLAB has also garnered prizes, like the Breakthrough Prizes in Fundamental Physics. And those are spread throughout the laboratory. So this is what is sort of known as the old lab, or the SNO part of the laboratory. It has utilities and services that are still today supporting a new phase of the SNO experiment I'll talk about later. This other part here that's more of a grid system, that's known as the new part of the lab. And it contains core areas like the ladder labs, which look like a ladder. They're intended for small to medium scale experiments. And then there are two large halls, neither of which is as large as the SNO cavern itself. So the cube hall is the second largest space, and the cryo pit is the third largest space. And without getting into the details of all of these experiments, I will talk about some of them in a moment. You can see that we're very full. Basically, every place you could stick a scientific thing in SNOLAB has, generally speaking, a scientific thing in SNOLAB. And if it's not being used for science, it's being used for a plant process, some industrial thing to support a scientific experiment, or it's being used for storage to stage equipment for a scientific experiment. So we're very busy, and part of this is what drives later what happens in the 15-year plan for SNOLAB. So let's talk a little bit about the various aspects and elements of the research program, and I'm going to begin with the environmental monitoring programs that we are running at the laboratory. Now, this is by no means exhaustive, but it is a sample of the kinds of things we do and why they're interesting. So like all places on Earth, Canada benefits from the fact that it has a flow of the atmospheric river over our heads. We are air breathers. We essentially live at the bottom of an air ocean on the surface of this planet. And just like ocean currents, there are atmospheric currents. And that means that things that start in one place can wind up in another. And for environmental monitoring, this is actually a huge benefit. So something that happens elsewhere within hours, weeks, or days, months, could drift over North America, and then wind up passing over or through areas where you can lay down sampling stations. So there are a series of atmospheric sampling stations located across the continent, and SNOLAB is one of the most recent recipients of air monitoring station and equipment that is typically used by the Health Canada program to do very sensitive radioisotope measurements. Now, why would you want to do this for environmental monitoring? Well, radioisotopes are everywhere, so they can already be used as a useful fingerprint of things that are happening. But in addition to that, there are some naughty things that people do, like detonating atomic weapons or building nuclear technology that maybe they don't actually have oversight on, or nobody knew that they were doing, or maybe there's a failure in a known nuclear technology. And environmental monitoring, atmospheric monitoring, can actually give you some early warnings that some of those things have happened. So there's also elements of for instance, monitoring the environment to enforce or assess compliance with things like the Comprehensive Test Ban Treaty, which is an international agreement banning the testing of nuclear weapons. So nuclear forensics is a key part of this. And for this purpose, we have a suite of instruments that we can use for this. So for example, in partnership with Health Canada, we have brought underground to the laboratory, to our low background laboratory area, a dual high purity germanium or HPGE detector system. So the idea is you have these two germanium crystals that look from either side. You put the sample in between them, and that sample will occasionally emit gamma radiation, which are really high energy photons, and the photons will travel and they will strike these germanium detectors. So you can look for things where two gamma rays are produced from a rare nuclear decay. And these coincidences are very powerful at rejecting random, uninteresting things that might just produce one gamma ray. This allows us to have the capability to count down to the individual level of atoms of various interesting radioisotopes that are only produced in human-made nuclear reactions. In addition to this, we've deployed these things called PIPS detectors within the same environment. These are specifically designed to detect electrically charged particles known as beta rays, fast-moving electrons. And there are nuclear processes that emit both gamma radiation and beta radiation in coincidence. This is, again, a very powerful tool for counting a very low number of unstable atoms in a sample, like an air sample. So the question we're trying to answer here is, can we fingerprint interesting phenomena in the environment using these radioisotope decays? Now, we also have capabilities on surface. So this is the air monitoring station I mentioned earlier. It's in our back overflow parking lot. So you can just walk by it every morning when you come into work. And this, again, here was installed by Health Canada, and it provides us with the ability to sample water and air, and then this information can be analyzed and sent back to Health Canada, including the samples themselves. So basically, we can do radiation monitoring, we can do water monitoring, air monitoring, and things like that. This is just an example on the lower right. Again, I don't expect you to squint and read all of this, but this shows you the level of gamma radiation that we're seeing in our back parking lot from this Health Canada station. It's typically at the level of 60 nanosieverts. That is a very, very, very tiny dose of radiation. That is what is known as a background dose of radiation, the kind that we experience every day. In order to get to anything even remotely interesting to a health agency, you'd have to experience 115 nanosieverts continuously for 1 year. And you can see we almost never get up to that for very long. There's this one interesting data point a few weeks ago where the gamma radiation count just kind of went up and came really close to that line, but then it fell right back down again. And again, you'd have to sustain that level for 1 year to be considered interesting by a nuclear regulatory agency of any kind, like occupational health standards and things like that. But this is a really sensitive capability for doing this kind of monitoring. And it leads to interesting questions like, what causes gamma radiation rates to go up and go down? Are there any relationships with weather, geoscience, anything like that? These are interesting questions that people could address. And this data is actually available through an open web portal. All right, so let's talk about a related phenomenon, and that's underground biology. And you'll see why that's related in a moment, because I've just primed you by giving you a sense that radiation is everywhere around us all the time. It's how we grew up on this planet. It's just a natural part of the Earth. Biological organisms are experiencing radioactive decays all the time, including you and me. I have radioactive potassium and carbon in my body, so I'm emitting a little bit of radiation all the time. This has interesting biological questions attached to it as well. And underground biology has become a booming field, albeit still fairly small, because of this. And so one experiment I want to highlight at SNOLAB is one known as researching the effects of the presence and absence of ionizing radiation, or repair. So the repair experiment's goal is to study the effects of ultra low or very low background radiation levels on living organisms. You and I and every other living thing on Earth evolved in the presence of some ambient radiation field. So the question biologically is, did biology take advantage of this to the benefit of those living organisms? In other words, do living organisms need some minimum amount of radiation to function normally or in a healthy way? This is the question that the repair team is trying to address. We know there is such a thing as too much radiation. Is there such a thing as too little? And the assumption for a long time was that less was better always, and zero was the best. But actually, these underground biology experiments here at SNOLAB and across the world are beginning to challenge that assumption. They have found evidence in small microorganisms that are deprived of the ambient radiation environment that they don't thrive as well as their counterparts in a normal radiation environment. There are more markers for carcinogenesis. That means that they're not as easily able to repair the damage to their DNA that might occur naturally in a living biochemical system. So the goal here is to scale up from small things to bigger things. There have been studies on lake whitefish embryos, for example. This project at SNOLAB has been a partnership between Laurentian University and Nossum University, which is the medical university in Sudbury and in Northern Ontario. And this is just one example of the kinds of things that they're trying to assess. One of the interesting things that they do is that they produce yeast both on the surface and underground in this shielded, very, very ultra low radiation environment. And then they can desiccate that yeast. It's still alive, but it's dehydrated. They can pack it up and they can ship it to other laboratories. And in fact, there's now a global effort across multiple underground laboratories to take the same desiccated yeast samples, ship them to different labs, run a controlled set of experiments over a period of the better part of a year. And at each stage of the experiment, send back a pack of the yeast that's been used in the experiment. And then the analysis is done the same way on every packet, regardless of where it came from or to whom it was shipped. The idea here is that biology is complicated. And to know that you're seeing a real effect, you have to know that you haven't biased yourself in some way. And so this massive global coordinated effort is an effort to remove any potential scientific bias in this, to really isolate the biological effects of ultra low radiation environments. This can be done in underground labs. Some of this yeast has been flown as part of NASA's BioSentinel program as well into space to look at the effects of radiation on, say, yeast that grew up in an ultra low radiation environment. So that's about biology, environmental monitoring. Let's get into some of the particle and astroparticle physics programs at the laboratory. And the big one right now, the one that has the most experiments underground at SNOLAB, is the hunt for the constituents of dark matter. So this is not a lecture on dark matter. This is going to be my one way of teasing all of this. But all I'm going to say, and there are many other talks that have been given at the Institute. You can go watch them online. They're great. They talk about the dark matter problem. They talk about specific experiments looking for dark matter. I'm going to give you a real family vacation photo picture of the laboratory program. But to motivate this, I want to start with really the key problem of dark matter and its constituents. And that is the only way we have ever seen dark matter do anything is through its gravitational interaction. It pulls on galaxies, it pulls on clusters of galaxies, it pulls on the largest structures in the cosmos. It affected the light left over from the Big Bang itself, the so-called cosmic microwave background radiation. It has left its gravitational imprint pretty much everywhere we have looked. But what we don't know is we don't know if there are individual bits of dark matter that are capable of interacting with individual bits of normal matter, the stuff we're made of, and do so through anything other than gravity. And because we don't know much about what might make up dark matter, you kind of have to look everywhere. And this little section here, this little axis I'm showing you, doesn't even begin to scratch the surface of the possible candidate, in this case, masses that could make up dark matter. Here, I'm talking about masses that go down to an electron volt and up to the level of, sort of a trillion electron volts, a TeV. This is actually a small part of the overall search space. You can go even lower than an EV, and then you're into the realm of what is known as axion search experiments. You can go above the TeV level, and then there's all kinds of interesting things that happen up there. I mean, dark matter constituents could be as heavy as planets, and we wouldn't have noticed them yet. So there's all kinds of interesting places to look, and that means there's a huge opportunity space. But covering an opportunity space like this is challenging. And the part of the space we cover at SNOLAB is we have experiments that are focused on the billion to trillion electron volt region for the most part. And right now, those targets are primarily made from liquids. But then in addition, we also have gas and solid targets that are much more sensitive to the region going up to a billion electron volts, but also down to about a million electron volts or so, even a little bit lower than that. That's only covering half of what I've shown you here, and it's only covering a tiny part of what's available. But this is simply to say that it is a rich portfolio of experiments out there, and SNOLAB has a piece of that portfolio, but this is a global effort to determine the constituents of dark matter. So in terms of liquid targets, I'm going to talk about the DEEP experiment and the PICO experiment program. I'll come back to those. And then in terms of the gas and solid state targets, I'm going to talk about for solid state super CDMS, DOMIC, and Sensei, and then for gas a program called NEWS-G. So let's dive into this a little bit. So let's start with solid state. So you take a solid object and you turn that into a target that dark matter could smack into. And the question you're trying to answer with something like the super cryogenic dark matter search or super CDMS is, can an ultra cold crystalline tuning fork sing when it's struck by particles, in this case, dark matter particles? And to answer that question, you need to make a nice crystal, in this case, germanium and silicon crystals that are about the size of a regulation hockey puck. And then you need to shield that from the ambient environment. Our lab, even though it's ultra clean and ultra deep, is still too radioactive for these very, very delicate instruments. So you have to shield them in copper and lead and plastic to keep out all the other things that are around. It's not harmful to people, but it's harmful to these experiments. And the theme I want you to walk away with at the end of this is, the reason we shower when we go to work underground is not because something bad has happened to us and we need to get it off our skin. It's because we've put something on our skin that if we get it onto these experiments, we ruin them. So it's actually we're the threat to the experiment. It's not the other way around. And it's not that the mine is a threat to us. It's really a wild problem that we're the problem and we have to acknowledge that. So this is the super cryogenic dark matter search. It is in a very late stage of construction. In fact, it's very near to beginning its operations. It does have a ticket to operate when it's ready at this point. It's gone through many reviews, and those reviews have gone extremely well. It occupies a part of the ladder labs area of the laboratory. This whole corner section back here, all of this is effectively devoted to the super CDMS experiment. I'll come back to this other thing called CUTE in a bit. But stay tuned, because the super CDMS experiment has been a decade to realize, and it is about to enter its operational phase if all goes well in the next weeks and months. Now, another way you can do solid-based detection of dark matter is you can essentially take a camera, put it in the dark, and have it take a picture of itself. And I know that sounds insane at the outset, but basically the technology that you and I and most other people have for camera phones, so these tiny little cameras you can hold in your pocket, this is known as a charged coupled device, or CCD. That's the thing that takes the place of old style film in these devices. And CCDs actually turn out to be really, really sensitive subatomic particle detectors if you cool them down and if you shield them from light and other things. So the theme of the CCD-based detectors, which are called DOMIC and Sensei, is that they are effectively cameras taking pictures of themselves in the dark. So you enclose them in a light-tight environment, you shield them with copper and lead and plastic and water to keep all that other stuff from getting in, and then you wait. You wait and you watch. And occasionally what you'll see is you'll see a pixel in the CCD light up, but there's no light. So it wasn't light that did it. And a lot of other things aren't getting in either. And so then you have to ask yourself, what made this pixel glow? And there are many possibilities. Of course, no CCD is perfect. Sometimes there's a little bit of uranium and thorium in there. So it could be that a uranium atom had a bad day, decayed, and then the resulting decay chain dumped a little bit of energy into one or more pixels in the CCD. That's not dark matter. We're not interested in that. But these instruments are so sensitive that they can actually tell the difference between that kind of what's called background process and then the potential interesting signal process. So this is what one of the CCDs actually looks like here. You see it's a very shiny little piece of material, and it's read out with electronics, and it's shielded inside of a copper box. And then all of that goes inside of a big pile. This tiny little thing goes in this big, over a human sized box of plastic, water, lead, and copper to shield it from us, to shield it from the lab environment. And results in extremely ultra-sensitive detectors that are very good at seeing lower mass candidates for dark matter particles. Now, gas. So the benefit of a gas is that you can use gases that are extremely light, like gases with hydrogen in them. Hydrogen is the lightest chemical element. And if you're looking for light dark matter, you want to smack it into something that is also equally low in mass. There's some basic introductory university level physics in this, but the bottom line is that to get a really strong collision effect, you need to put a target in front of dark matter that's maybe more commensurate with its own mass in order to get a really big effect from the collision. This is an example of one of these gas-based detectors. It's called NewsG. And it's really an amplifier for the subtle notes that would arise from dark matter's plucking of the gas. So if dark matter gets into this detector and it smacks into a hydrogen atom in the gas, this can actually displace the hydrogen nucleus from its electron. And when that happens, you suddenly create electric charge where there was none before. And then the sphere in which all this gas is held, it's at high voltage. So its job is to then avalanche that effect and magnify it. So it's an amplifier for these tiny, subtle little interactions. A great deal of effort goes into removing electronic noise, improving the design of the electric field in this. This is an ongoing R&D program that's also delivering science as it goes. Now we can get into the liquids. So the liquid targets, the liquid noble target, for example, using liquid argon is deep 3600. You can think of this as a liquid lamp that shines when it's struck by the dark. So if dark matter gets in and strikes an argon atom, it actually creates a cascade of light in the process, and we can actually pick up that light with photosensors, with photodetectors, things that see light. Deep is their target holds about 3,300 kilograms of liquid argon when full, and it's just concluded a series of important upgrades to the experiment that will make it even more sensitive, and they have moved into their next operations phase at this point. Now, because they're using argon, argon is a heavier atom than, say, hydrogen or something like that, so they tend to be more sensitive to higher mass dark matter candidates, so something a little bit more up the sort of mass ladder I showed you earlier. And then there are superheated fluid targets. So instead of using an ultra cold cryogenic liquid, this one actually uses a fairly hot liquid. I mean, it's not boiling. It's boiling for its own properties, but it's not boiling compared to, say, a cup of water. The target of choice has been usually freon, which is a refrigerant. So freon is normally a gas at room temperature and pressure. So we have to put it under pressure, and we have to heat it up. It's actually a little bit lower. It's about 13 centigrade. So it's below room temperature, which is about 20 centigrade. So it's actually cold compared to room temperature, but it's real hot for freon. And the freon can be put into this liquid state, and it's a very subtle liquid state. It's what is known as superheated. So it remains liquid, but if you put even the tiniest bit of energy into it, it will boil. It will make bubbles. So you can think of these superheated fluid targets, fluid detectors for dark matter as a little bottle of freon that boils at the slightest touch. And what's the slight touch? Well, we hope it's dark matter. If dark matter strikes a nucleus in the freon, it can create a bubble. We can very quickly image the bubble. We can hear the bubble from its sound waves. And then we can press on the liquid to get the bubble to go away. And then we can gently unpress on the detector, and we're ready for another interaction at that point. So we've been operating Pico 40L, which is 40 liters of freon. It's about 70 kilograms of freon. That's in operations. And we're working on the construction of Pico 500, which is actually 250 kilograms of freon. It's in the largest set of fused quartz silica jars that industry makes. So we're limited by the size of these glass jars that you can see here on the left, faintly in this picture and much more clearly in the right picture. That's what we use to contain the freon, is in between a pair of nested jars. So this is a very big project, and it's been very exciting to see this come together. So Pico 500 is, there are major pieces of it that are already in place. The steel pressure vessel that will hold the glass detectors inside of it, that was actually brought in pieces underground and welded underground in the clean lab at SNOLAB. And if you're curious about that, ask me at the end. That's done. It's been pressure tested and verified for its pressure rating. And you can see here the team on the left during a test assembly of what's called the inner detector. That's the part that has the jars that hold the Freon. And there's some delicate, both manual maneuvers to get things into place, and then there are mechanical maneuvers using custom designed instrumentation so that humans never touch this thing. It is a touch-free assembly process for this. But that is really, really challenging for something this big. These jars are, bigger than a person at their largest size. So there's a lot of underground activity for Pico 500. Construction will proceed through this year and next with the goal of starting operations in late 26 or sometime in 2027. So finally, on the research side of things, I want to talk about our neutrino program. We have two major experiments at the laboratory for studying this elusive neutrino particle, the electrically neutral cousin of the electron. And the flagship of this is the SNO+ experiment. So the original Sudbury Neutrino Observatory was built to answer the question, do neutrinos change from one known type into another known type? And indeed, the answer is yes. This turns out to imply that neutrinos have a non-zero mass. They possess substance in the same way that you and I possess mass, and it's tough to get us moving without having to push hard. Neutrinos also have a teeny tiny bit of mass, and that actually means you don't get to push them around for free. The question, of course, then is, what is the mass? Neutrino oscillations themselves can't answer that question. You have to do other experiments. And one way to do this is to look for an ultra rare nuclear process where you produce two neutrinos and two electrons from the decay process. Now, if the neutrino is of a certain kind, then you will actually always get two electrons and two neutrinos. And in many nuclei, that process has been observed. But if the neutrino turns out to be special compared to its cousin particles, if it turns out to be its own form of antimatter, and that when a neutrino touches another neutrino, they actually annihilate each other. If it turns out that that's the nature of the neutrino, then you can have something called neutrino-less double beta decay, where you get two fast electrons coming out of the nucleus and no neutrinos because they've annihilated each other. That would be ultra rare. And to see it, you need shielded detectors capable of seeing very rare things, maybe a few events in 10 years. That's crazy, but that's the kind of experiment that we have been building and will continue to try to build into the future. SNO+ is one such experiment. So it has a 12-meter acrylic vessel inside of which it can hold a target liquid. That target liquid right now is a liquid scintillator. It's actually effectively an ingredient that goes into many detergents known as linear alkyl benzene. You can actually then try to put a material into the linear alkyl benzene that can experience this neutrinoless double beta decay. So whereas historically SNO and SNO+ have been looking for neutrinos coming from outside the detector and getting in, the final phase of the SNO+ experiment is to put a neutrino emitter, or maybe one that doesn't in fact emit neutrinos, into the center of the detector and look inward to see if you see this process. And the material of choice is tellurium-130 because it's readily ripped out of the ground, and it has a very abundant 34% naturally abundant form that could experience this neutrinoless beta decay process. And there's a lot of chemistry that goes into this. Basically, the question that SNO+ is really trying to address here is, can we make a metal dissolve in a detergent, and in doing so glimpse the mass of the neutrino? It's a crazy question, but it's also awesome, and this is why people love these experiments. So they've got to get tellurium, a metal, to want to float inside of a component of detergent. And that's a difficult chemical process that industry isn't generally interested in solving. So this collaboration had to solve that chemical problem, and in fact has. So now they're going into an industrial phase where they produce a lot of the special tellurium molecule that can dissolve in this linear alkyl benzene detergent component. And I'm showing here just a few pictures of the plants that are used at the early stage to wash and clean the tellurium in the form of telluric acid, and then later to synthesize it into this special molecule, which is known as T-diol. That's the molecule that can then be loaded into the scintillator. And they're effectively now in their production test batch operations phase for these. So SNO+ isn't just trying to do neutrinos double beta decay. I won't be able to spend a lot of time on this, but they are in fact a science machine. They have publications stemming from a phase where they ran with water inside of their acrylic vessel. That was from 2017 to 2019. And more recently, they then filled with linear alkyl benzene. They did a partial fill, which was stopped by the pandemic, but then they completed that fill. And that's 2019 to now. And they've been rolling physics results out of those programs as time has gone on. These are challenging measurements. So for example, they've recently made the first observation of boron-8 solar neutrinos interacting with carbon-13 inside of the detector. So these are, ultra rare processes that they are capable of probing, and they can do all of this, as they build up to this tellurium loading phase, which is effectively imminent. And then finally, the second experiment that we have that's dedicated to neutrinos is the one that Jarrett mentioned in the opening, and that's the Helium and Lead Observatory, or HALO, which I co-lead with Dr. Clarence Virtue. And the question we're trying to answer there is, what can recycled lead and helium teach us about exploding stars? So neutrinos will interact in lead. And when they do that, they produce neutrons. And now the trick is, can you see the neutrons from those neutrino interactions? When a star goes supernova, it produces a huge number of neutrinos. Even far away, there will still be a vast number of neutrinos that pass through this roughly 3 meter by 3 meter by 3 meter stack of lead and helium underground at SNOLAB. And what we expect is, over about 10 seconds, as that neutrino blast wave passes through the detector, we will see 4, maybe 5 or 6 interactions of neutrinos with the lead. That is very uncommon in this detector. We do not usually see things like that happening, and certainly not over 10 seconds. So it's a fairly unique signature, even though it sounds like there should be a lot of things that make neutrons, and there are, but they don't make a lot of neutrons when they happen. So we're using 79 tons of recycled lead from a cosmic ray observatory and 128 recycled Sudbury Neutrino Observatory neutral current detectors. Those are really beautiful detectors that are filled with helium-3. The real hallmark of HALO is that we have a greater than 99% uptime, and we are the longest continuously running experiment at SNOLAB. We've now been going strong for 13 years, and we are astronomically patiently waiting for a star to blow its top in our half of the Milky Way. Astronomers have never seen the beginning of an explosion from a Milky Way supernova. The neutrinos arrive a few hours before the light. So we are an early warning system, and we're part of the Supernova Early Warning System, or SNOOS, that is supposed to tell astronomers, okay, we think a blast wave from a supernova. Based on the triangulation across the globe using these detectors, we think you should look here. And that way they know where to point their telescopes. Otherwise, they wouldn't know where to look to see the light. So finally, what I would like to do is talk about very briefly about the research program we have with quantum computing components, or qubits, underground. So I mentioned earlier, there's this thing next to Super CDMS called QUTE. QUTE is the Cryogenic Underground Test Facility. It is effectively a place where you can stage a small experiment inside of an ultra-cold dilution refrigerator, which can then be put inside of a water shield tank. So it is an R&D playground for ideas that need to be tested before they might go into a much more expensive, more serious experiment. So QUTE provides basically a bunch of system components, a class 200 clean room for installing your experiment into the dilution refrigerator. Then the dilution fridge can be sealed up. It can be craned up and lowered into this water tank. And then you can operate the experiment from the water tank. And one of the things that we're currently operating underground are a series of quantum bits, or qubits. These are the core elements of future quantum computers. Quantum computers currently on the surface of the Earth are only good. They can only hold their critical computing state for maybe 10 seconds before they go into a fault mode. These faults are interesting. There are many reasons they happen, but we believe part of the reason that this happens is that cosmic radiation raining down on the surface of the Earth can upset the qubits. This happens with normal computers, so why wouldn't it happen with quantum computers? So the question we're trying to answer is, if we take those qubits and we run them underground in a dilution fridge 2 kilometers below the Canadian Shield, does that improve their operational characteristics? And what does that then teach us about shielding them or operating them differently up on the surface? So that's the question we're trying to answer with this. And it's been an interesting journey. We've only just gotten the qubits underground in the last year, and the team is analyzing the data that came from the first run and has already planned more runs of the qubits underground. All right, so finally, let me close with a 15-year plan for SNOLAB. So you've seen some of the portfolio. It's very rich, it's very dense. And the idea here now is to look to the future. So the 15-year plan for SNOLAB, the question, of course, is why now? And the answer is because we were tasked, Canada tasked itself with a decision-making framework that was introduced in the 2024 federal budget. The goal there was to support something called Canadian Major Research Infrastructures. There are 6 research facilities that were introduced as part of this framework, and SNOLAB is one of them. The Canada Foundation for Innovation, which is the foundation that primarily funds SNOLAB, then required the construction of a plan that assessed long-term capital and operational needs of each of these facilities. So we needed to look to the future. We needed to be serious about what kinds of budget scenarios that might require to do various things. And as you can imagine, we were asked to provide a fairly detailed and reliable budget estimate as a result of this, and understand the conditions of our assets now and going out 15 years under 3 different budget scenarios. One of the scenarios is maintaining the current level of operations. The other one is fully supporting the Canadian research community. And then finally, increasing global competitiveness. That's how the scenarios were framed for us. So there was room to understand within each of those what that meant to each facility. So there was a process for this. I won't get into gross detail about this, but it was a lot of engagement and consultation. So there was first staff and engagement and consultation within the laboratory that started in late 2024. In early 2025, it began to open up to input from what we call our user community. We have about 1,200 users at any one time. These are non-staff individuals that take advantage of SNOLAB to do experiments of various kinds. So we needed to hear from them, what did they think was going to happen in the next 15 years? We actually had a formal workshop in late April, early May of 25, the Future Projects Workshop, when we generated an 80+ page report from that, which you can find for free on the archive. I've put the number here. And then finally, there was a town hall at the Canadian Association of Physicists meeting in June of 25. Then there was a presentation of findings at the Arthur B. McDonald Canadian Astroparticle Physics Research Institute's annual community meeting. This is also shortened to the McDonald Institute community meeting. And then finally, the plan was formally submitted to CFI in September of 2025. And what's in this? The major components of this, there are many more things than I can go into in the last minute of my presentation here, but there were key things that emerged out of all these conversations. First of all, having a surface building that is behind the industrial control zone of a mine is a challenge to many users. You have to do a lot of training just to put one boot on that site. And so we began to realize that there'd be a benefit to us having an additional surface complex that wasn't within the industrial control zone, but was close by, so that it's an easy decision to say, I'm going to work at one site or the other, or I'm going to move between sites. So in all scenarios, we proposed the construction of such a building similar to the existing one on site, with a large auditorium space to accommodate our current staff and programs, and new spaces for training and laboratory work. That was in all scenarios. In the second and third scenario, we saw more. So the plan in the second scenario, as we meet the needs of the Canadian community, is more lab space, 2 more floors of office and collaboration space, a visitor center so we can more easily welcome the public in to engage in SNOLAB, and a dedicated warehouse on that site for storing more critical components and staging them for deployment to the underground lab. And then finally, in scenario 3, to meet the needs of the global community, daycare, a cafeteria, a separate hostel facility so that people have a place to stay. Housing is always a challenge in Sudbury. We have staff that have helped to ease that stress, but it's still not perfect. And having a dedicated hostel facility would go a long way toward helping with that. And in addition, materials fabrication capability. And then, of course, the crown jewel of the laboratory is the underground lab. And in scenario one, we would refurbish and enhance the capabilities of the existing laboratory. That's shown in light gray in the map here. So that's the map I already showed you before. But in scenario two, to meet the needs of the full Canadian community, we recognize that we're already tight on space and we need more space. So the idea would be to build additional space for small to medium scale experiments and for the storage of critical components like liquid argon or liquid xenon for any future experiments that may need lots of that material, for example. In the third scenario, to meet the needs of the global community, we envision an additional expansion on top of this that provides a large hall in addition to additional drift spaces where experiments and materials can be staged and built. That large cavity, to put it in context for an audience from, say, the Institute for Underground Science here at SURF, would be about half the size of a dune cavern. That's sort of the scale we're thinking, but of course, this is still looking many years out. And we know there are experiments already that are interested in space like that, so we know that there would be demand for something like this in this phase. So finally, let me conclude an outlook and get to the questions here. So of course, SNOLAB is a very vibrant, very busy laboratory, but nevertheless, we always welcome opportunities to cross disciplines more in order to solve these challenging problems at the frontiers of all of our fields. We engage in strategic planning, community engagement, and this has really culminated recently in our 15-year plan. The problems of this century, be they in biology, chemistry, astrophysics, nuclear physics, whatever, they're going to benefit from a combination of many experts with varied perspectives, and we are aiming to facilitate this as a laboratory. And I can't say enough good things about the SNOLAB staff and the user community for all the work they do, the staff especially for the logistical and planning and technical, all the other work, the cleaning of this laboratory to maintain this crown jewel Class 2000 clean lab space underground in an active mine. I can't say enough good things about all these people, and I hope you're interested in partnering more with us. So I will just say at the end here that we strive to ask questions, to seek answers, and go deep. So thank you very much.
Dr. Sekula, thank you so much for this eloquent update on science at SNOLAB. Let's see if there are any questions. Let me jump in with one question that I suspect some of our audience is interested in. In the news recently, there was a mining-related earthquake or seismic event in the Sudbury region. Thoughts and hopefully everything survived, but happy to get an update on that particular element.
Yeah, and I'm happy to provide it. So yeah, indeed, it's been a very interesting last 3 weeks at the laboratory. There was back in late October, early November, there was what was publicly been reported as a magnitude 4.0 seismic event in the Creighton mine. It obviously, everyone, when that happened, went to what we call the refuge. The refuge is actually the dining area of the laboratory. So everybody reports immediately in an event like that to the refuge space. Everybody was accounted for. Nobody was injured. And by close of business on that same day, everybody was brought back to surface safely and went home. So the big picture thing was that the people involved in SNOLAB, which are the heart of the laboratory, everybody was fine. The laboratory was built in a part of this rock that is designed to be extremely stable. And so in the event that inevitable things like seismic activity occurs all the time in an active mine, we are in one of the best located places in the entire complex. And as a result of that, the laboratory itself, the clean lab, suffered no damage that we have been able to find. Certainly it shook dust down from places where we just aren't normally able to reach it. So there was a big, massive cleaning campaign the first week we got back into the lab. So again, kudos to the cleaning staff, and then kudos to all the staff and users who pitched in at their experimental sites to do extra cleaning and extra pickup just to get that little layer of new dust off of tables and floors and wrenches and hammers and things like that. We did have damage to one of the plant facilities that's located outside the clean lab. Basically, our air conditioning system went down. So the fact that the lab heated up to ambient rock temperature, which is about 30 centigrade, that was a bit of a challenge. That put stress on many pieces of equipment and some of the experiments in the laboratory. So the community is still working through that at this point, but the air conditioning system, the chillers are back up and running. We're at stable operations again. We've had folks back in the mine now for a week under normal working circumstances. And we're looking ahead down the road now to what we need to do, not only to address the things that did happen during this event, but to think ahead to if this is going to happen every 20 years, which right now seems to be the rhythm of this. The last event of this scale was back in 2006, just a day or two after snow stopped running, in fact. If this is going to happen roughly every 20 years, we just need to look down the road and think about, in the context of our 15-year plan, for example, what additional needs are there in the short term, medium term, and long term to make us even more resilient than we already are. And it turns out the lab is very resilient already.
Remember the 2006 event? It was interesting.
Yes, it is. The analogy I would give anybody is, if you want to know what this is like, the best example I can give you is put your head inside of a really big, like, church bell and then have somebody hit it with a hammer. It is not pleasant, but it is obviously survivable, and it is off-putting. It was a very, no one expects that to happen, right? So it's very loud when it happens. And so that obviously was a surprise to many people. But again, I'm impressed by the resilience of our staff, our users, our whole community, and certainly of the laboratory complex itself.
Very good. There's a couple questions in the chat here. Let me go to Vimal Kumar. Let me unmute you so you can ask your question. Go ahead.
Thanks for sharing the mic. I'm just curious about the radon level, how it is controlled inside the laboratory.
Yeah, that's a great question. So the short answer is that the radon level, generally speaking, inside of the laboratory is the radon level that you would find in your average Ontario basement. So basically, just to help the audience out here, radon is a noble gas. It's a noble chemical element. It is the only naturally occurring radioactive such element that is gaseous. And it's produced as a byproduct of uranium and thorium decay. And uranium and thorium are everywhere in the rock of the Earth. It's, in fact, how we date the age of the Earth is we use the relationships of these decaying radioisotopes as clocks. So radon, the minute you dig a hole in the ground, you start encountering more radon because you are now more surrounded by decaying uranium and thorium that's just in the rock. So you make a basement in Ontario, you go down into the rock, that gas can seep through the walls naturally. It can get through little cracks, and it can even diffuse through thin materials, and it can get into your basement. And because it's heavy, it tends to collect in those lower environs. And so a very standard thing in an Ontario basement is a radon removal system, which is just a little fan that blows the gas back out into the environment. So we have pretty much the same level of radon in the lab that you would find in a basement in Ontario. That's not great for sensitive experiments. So it's perfectly fine for humans because it's not above the risk level for a human being, but it's absolutely not great for many of our experiments. Radon is one of the chief enemies of dark matter and neutrino searches, especially at this ultra sensitive level. Radon, just like it will get into your basement, it will get into your experiment. It will work its way through thin copper. It's a gas. It will go where other gases go. And so you have to work very hard to make sure that radon isn't implanted in any material you use to build your experiment. So one thing you do is screen your materials to make sure that they don't have a lot of uranium and thorium, because if they do, they will make radon. So you screen out those radioisotopes. You shield against it. And we also have radon removal systems. So a great example of this is the radon removal system that is used for the construction process of the super CDMS detectors. Those hockey pucks, they're assembled into stacks that are called towers. Those towers are then loaded into the refrigerator, and then that refrigerator, they're loaded into a structure that's connected to the refrigerator. That structure goes inside of the shield for super CDMS. When you're doing that assembly, you want to do that assembly in a very low radon environment. So there's a special clean room dedicated to super CDMS that's right next to the detector where they do that work. And they have a series of charcoal filters and these very industrial looking plants. That's one whole hallway in the map I showed you. Let me see if I can go back to that. So that's going to be back here. So in the map here we go. So in this map, there's this clean room, and then there are all these plants here, and part of the plant systems in this map here are for scrubbing the radon out of the air that goes into the clean room. So they reduce the radon by over a factor of 100 or about a factor of 100 before it goes into that. It's a much cleaner environment for doing this sensitive instrumentation. We don't do that lab-wide. We only need to do it in a few places. We do it on the PICO experiment as well. I think I can scoot ahead here to PICO, and you'll kind of get a sense right away. So yeah, so you see the team here, right? The team is doing this work on the inner detector vessels. And if you look closely, you'll notice this like plastic walls back here. They're actually inside a clean room in the clean lab. So that's even lower dust. And then in addition, these jars are kept under a purge of gas that's very low in radon as well to keep the radon out. So you can pump gas at high pressure into the enclosure that holds these jars. That keeps the radon from getting onto the surface and leaving behind nasty radioisotopes that mess up a dark matter experiment. So there's all kinds of ways we try to mitigate this hazard. It's not a hazard to humans in the underground environment. It's a hazard to these sensitive detectors. So I hope that helps.
Thanks, Dr. Sekula.
You're welcome.
Maybe one final quick question as we close out. Really looping back on your strategic plan, you submitted the document in September. Maybe a quick couple comments on next steps. The funding agencies are going to write you a check when?
Yeah, well, I mean, wouldn't anyone like to know that in any country, right? So, well, we're now in a holding pattern at this point, right? So we have submitted this plan to CFI. There was some preliminary back and forth before the final submission of the plan to get a read on whether or not the plan itself addressed the questions in a way that was useful to the Canada Foundation for Innovation. Now, the government has just tabled, and in Canada, that means put on the table, not taken off the table. The tabled means something different in US and Canada, as I learned when I moved here. So they've put their budget on the table for the next year. That's going through its own parliamentary process right now. And if that budget does in fact firm up and that budget proposal becomes a formal budget, we might know more at that stage about what the next phase of this, I'll go back here, this Canadian Major Research Infrastructures program might look like. In the 2024 budget, it was just a paragraph with a concept in it. That concept was then turned into this process so that CFI could gather information from these 6 entities about what would it look like to then meet the needs of the current program at these facilities, the Canadian needs at these facilities, and the global needs at these facilities. So they have that information now, and presumably that would be turned into actionable items somewhere down the road. But that timeline is not something that we control. And we respect that we've provided information to the process, and now a process must occur. And we will see how that goes. And I'm sure there will be conversations as that process unfolds between the laboratory and the funding agencies. And the province also provides funding to support SNOLAB, but CFI is by far the largest funding stakeholder. So we'll have to see how that plays out at this point. We're very much we're in the middle of a process that is new for Canada. This is the first time anybody's asked for a 15-year plan for these facilities. So this is new territory, but we're very positive about the fact that this kind of scope of vision was requested.
Very good. Very exciting. Well, fingers crossed.
It is very exciting. I agree. Yeah.
Alrighty, well, let's wrap things up and thank Dr. Sekula again. And as a reminder, this talk is available to view and share on YouTube, Vimeo, and institute.surf/deeper-talks web pages. Next month's Deeper Talk will be on December 10th at 9 a.m. Mountain, our usual slot. The topic, measuring dijets from ultra-peripheral heavy ion collisions, with featured speaker Dr. James Bowen. Your feedback helps improve this program, and we appreciate any suggestions for speakers and topics for future talks. Please fill out the short survey you will receive immediately following the talk on your Zoom and in your email. Thank you.